17.7 deals with the common ion effect in salt solubility equations. So we already talked about the common ion effect in the context of buffers and acid-base reactions, where if you already have some product present, perhaps because of a different soluble salt being added to the solution, well, that's going to have a huge effect on where the equilibrium position lies. When it comes to salt solubility, what it means is that if you already have one of those ions present, then it will suppress the amount of the sparingly soluble salt is going to get dissolved into a solution. It will lower the molar solubility, or in other words, the molar solubility in pure water is different than the molar solubility in solutions which already contain common ions. Okay, we'll see this in action. It'll be apparent when we construct an ice table. And so let's just look at an example. NaCl is a soluble salt, according to our solubility rules, but it actually does have a K value. The KSP for sodium chloride is 37.66. So it's a large number, it's product favored, a lot of sodium chloride can dissolve into water. And maybe it's worth it really quickly finding the molar solubility of NaCl in pure water. Okay. We know that the KSP is going to equal x squared for a simple salt like this. And so the square root of the KSP is going to be the molar solubility. Okay. So let's just quickly find that. SQRT of 37.66. It looks like you can get about 6.137. We get 4 sig figs with this. That's nice. 6.137 moles per liter. 6.137 moles per liter of sodium chloride in pure water. Okay, well, what if instead of pure water I have a hydrochloric acid solution and it's 12 molar HCl? Now, hydrochloric acid has a higher solubility, apparently, than sodium chloride. I can fit 12 moles of hydrochloric acid in every 1 mole of water. But hydrochloric acid is a strong acid, so what this really means is that I have H+, I also have Cl-, and this is the ion which is shared in common with sodium chloride, our soluble salt of interest. So let's write the ice table. NaCl solid dissolving into Na plus Cl minus. And we still have no sodium to begin with, but in this case, because I'm trying to dissolve my sodium chloride into a hydrochloric acid solution, I start with 12 moles of chloride ion. We'll still get plus x and plus x, and so here we end up with x and 12 plus x. Okay, so let's go ahead and solve this. Our solubility product there, 37.66. I should have moved that over. Can I go ahead and erase all of this? We don't need to know all of that. Okay. So I know that 37.66 is going to equal x times 12 plus x. Okay, well, it would be nice if we could assume that this x is small. Let's at least start out with that. Is this x small? Then we could just take 37.66 and divide by 12. 37.66 divided by 12. And that's going to be 3.13. And unfortunately, 3.138 divided by 12 times 100. That means that x is, over 1/4 the value of 12. So probably we're going to have to solve this quadratically. And I don't necessarily want to go through the quadratic formula. So I'm just going to solve this using an algebraic solving tool like Wolfram Alpha. So here I am at Wolfram Alpha, and I'll just put that formula in. 37.66 is equal to x times 12 plus x, and we'll see what sort of values we get. There we are. And so we get a value of x is equal to about 2.58. And if we go back and compare that to what we had before, what was it? 3.14. So the 2. Oh shoot! Now I've forgotten what it was. 2.58 is definitely different. It's definitely important that we did the quadratic formula there. So x in this case is going to equal 2.58. I guess we get 4 sig figs. 2.583 molar. Okay, so in other words, sodium chloride has molar solubility of 6.137 molar in water, but only 2.583 molar when you have hydrochloric acid at a 12 molar concentration as your solvent. This is going to be especially important when it comes to the solubility of hydroxides. So let's consider something like, oops, I want to go back to our table. Uh-oh. Okay, so back up a bit here. Okay, here we are at our table of some solubility products, and some hydroxides like sodium hydroxide, potassium hydroxide, they are readily soluble. But you see, there's quite a few here. Say manganese hydroxide, or let's see if we can find the worst one. This mercury 2 hydroxide, for example, is a good candidate. Or if we look on the previous page, there's we'll just stick with this mercury 2 hydroxide, okay? So it has a solubility product of 3.6 times 10 to the negative 26. And if we just solve that naively, then we would say KSP is going to be equal to x times 2x squared, right? And that's going to be 4x cubed. And so we'll get a value of x equal to the cube root of KSP over 4. So we're going to have to approach this problem by taking the cube root of KSP divided by 4. Oh, and what was that value of KSP? I'm sorry, I'm having technical difficulties today. 3.6 times 10 to the negative 26. Negative 26. Okay. So we're going to take 3.6 e negative 26, divide that by 4, and raise it to the power of 1/3. And we get 2.08 times 10 to the negative 9th. So x is equal to 2.08 times 10 to the negative 9th. And 2x is going to be our OH minus concentration. And that would equal, what, 4.16 times 10 to the negative 9th. And that would imply a pH of 14 plus the log of the OH minus 4.16 E negative 9. That would imply a pH of 5.62 for this mercury 2 hydroxide solution. Now let's stop and think a minute. If I start at a pH of 7, neutral water, and I add some mercury hydroxide, the pH ought to go up. Maybe not by very much because it's a sparingly soluble salt, but there's no reason for the pH to go down. So what has happened here? What has failed us? Well, we actually don't start with a zero amount of hydroxide ion. And so this relation here isn't going to work. We're going to have to actually do the ice table here. Considering that we have initial amounts of hydroxide even for neutral water. It's going to be 1 times 10 to the negative 7th molar, right? That's the amount of hydroxide in neutral water. And so now we'll get plus x and plus 2x. And now we're going to get x and 1 times 10 to the negative 7th plus 2x. And this really changes things. And so 3.16 times 10 to the negative 36 is going to be x times 1 times 10 to the negative 7th plus 2x squared. And what we'll do is we'll hope that x is small. I'm actually not entirely sure how this is going to work out. But if x is small, then x is going to equal 3.6 times 10 to the negative 26 divided by 1 times 10 to the negative 7th squared. And we can go ahead and do that in our head because they're all just powers of 10. It should be 3.6 times 10 to the negative 12th, but let's double check it just to be sure. We have 3.6 e negative 26 divided by 1 e negative 7 squared, and 3.6 times 10 to the negative 12th. So x, I'm running out of room here, x is equal to 3.6 times 10 to the negative 12th. Now that definitely is small compared to 10 to the negative 7th. That's a factor of 100,000. And so our assumptions are good. And that means the pH is essentially unchanged. You know, this 10 to the negative 7th is a whole lot more hydroxide ion than we're going to see here. And that the molar solubility of our mercury hydroxide is actually a lot lower than we would have expected. Okay, that's for neutral water. Well, what about if I have the pH controlled by the presence of other acids or bases? If I have mercury hydroxide that's going to be in something like 1 molar hydrochloric acid, well, that's going to change things. So we'll say in 1 molar hydrochloric acid, we'll still get plus x, and here we have 1 plus x. Well, we can suspect from Le Chatelier's principle, did I say hydrochloric acid? Sorry, I meant 1 molar sodium hydroxide. So we have a lot of hydroxide already present. Le Chatelier's principle says that's going to push more toward reactants. We'll expect a lower solubility, and indeed the math gets very simple. If we have 1 molar sodium hydroxide, then this x becomes 1 plus 2x squared, and that 2x is going to be small, so that's just a 1 squared. And what's 1 times 1? It's 1. And x in this case will just equal to KSP. The molar solubility of mercury 2 hydroxide in a solution of 1 molar sodium hydroxide is 3.6 times 10 to the negative 26 molar. It's going to be a very small molar solubility. And what if instead of 1 molar sodium hydroxide, we had 1 molar hydrochloric acid? Well, if hydrochloric acid is at 1 molar, then that means that the OH minus concentration would be at 10 to the negative 14th molar. Right? In a strong acid, the hydroxide concentration is very, very small. Well, in this case, we could say that we have 10 to the negative 14th, 10 to the negative 14th plus x, and we'll get our KSP is equal to x times x plus 10 to the negative 14th squared. And here we'll actually say that x is large. It's this 10 to the negative 14th, which is small. And so this reduces, oops, that'll be a 2x. All this time, that should have been a 2x. And we'll end up here with the KSP is equal to 4x cubed like before. And I've actually forgotten what that number came out to be. It was something like 10 to the negative 9th. I bet it's still on here, right. 2.08 times 10 to the negative 9th would be the molar solubility in acid. And so we see that in neutral water, that's down here, 3.6 times 10 to the negative 12th. In 1 molar sodium hydroxide, it's 3.6 times 10 to the negative 26. And in 1 molar hydrochloric acid, it's 2.08 times 10 to the negative 9th, 1,000 times greater solubility. And if we moved up to like 12 molar hydrochloric acid, it would have an even greater effect. So even these insoluble hydroxide salts can often be readily dissolved in acidic solutions because acidic solutions drive that hydroxide concentration down so low. And thinking of Le Chatelier's principle, by having the acid removing so much hydroxide, that's going to push the rest of the reaction forward and actually improve the molar solubility.